Hey everyone, welcome back to Calc 3. This will be lecture 23 of the course. And in this section we're going to build on our double integral applications. And we're going to look at using double integrals to calculate the surface area of a surface in three-dimensional space. So let's go ahead and jump into it, and we'll call this section 4.4 surface area. Okay, so let's consider, we're just going to kind of work, as per usual, we're going to work up sort of the construction of these things and try to get some insight into how integration allows us to solve this particular problem. So let's consider a function of x and y, z is equal to fxy, and of course this is going to produce some surface in three-dimensional space. So we're considering the function and its surface, which we'll denote by s. Okay. Now let's assume some things about f. Let's assume that f is defined over some region R. Okay, so of course we'll have to assume that f is defined on a region R. We're going to assume that R is closed and bounded, right? Got to have boundedness for sure here, closed and bounded. And then we have to also assume that f is differentiable, meaning that it has continuous first partial derivatives. So f is differentiable, okay, meaning that it has continuous first partial derivatives. Okay. All right. So we're talking about a function f on a region R. The region is closed and bounded, and f is differentiable. Okay, so what we want to do is we want to be able to find the surface area above this particular region. Okay, and so let's draw a picture. Let's draw a picture, and I'm just going to do the best I can here, as per usual. Okay, so we're going to have this function here, living in three-dimensional space. Okay, we'll say that this is our z-axis over here. We've got our x-axis coming off like that, and then we've got our y-axis over here. Okay, and so in the xy plane, we've got this region R. Okay, so this is not a terrible drawing yet. It's pretty good. Okay. So what we're interested in doing is we want to know the surface area of this surface that lies above R, right? So this is R. Okay. And so what we're going to do is, as we typically have to do with double integrals, we have to create some kind of a partition of R, right? And in this case, we're going to use rectangles, okay, just like we saw in previous examples. So we're going to partition up this space R into n rectangles. Okay. Now the area, of course, the area of each rectangle is trivial, right? It's going to be, so if you have some region here that we're talking about in particular, let's call this Ri, it's a subregion Ri, then the area of each rectangle is trivially, it's going to be xi, yi, right? So delta xi, delta yi in this case. Okay. Okay, so we've got this region here. This is the domain of our function f, and it's a rectangle, so it has this area. Okay, so then in each Ri, we're going to, let's identify a point. So in each Ri, let xi, yi, and in this case, we'll say it's the point closest to the origin. It doesn't matter though, ultimately. Right, but if you have some sense for what defines each xi, yi, it can be helpful. Right, but so for each Ri, let xi, yi be a point in the square, and we're going to say it's the point near the origin. Okay. Now what we're going to do is we have to somehow extend this idea of area up into the surface. And so at this point, xi, yi, so at the point xi, yi, actually I want to write it like this. I want to say at the point xi, yi, zi, right, because it's a point on the surface. And this is, of course, we know where the zi comes from, right? It's xi, yi, f of xi, yi. Right? So at that point on the surface, S, we want to construct a tangent plane. Okay, so we're going to construct a tangent plane. And we'll call the tangent plane Ti. Okay, so what are we talking about here? Let's come back into our drawing here. So I've got some point, right, in Ri. And if I think about where that point goes up to the surface, right, it's going to be right here, we'll say. Okay, now at that point on the surface, I want to create a tangent plane. It becomes kind of challenging drawing these things, but maybe it looks like that, right? Okay. And so the area, now here's kind of the tricky part of this idea, right? So the way I've drawn it isn't perfect, but what you would imagine here is that the tangent plane can be restricted to the area that's directly above the region. Okay, right, so this is it's drawn a little bit out of proportion here, but you can imagine if I can construct a tangent plane there, no problem, but then what I need to do is I need to constrict the tangent plane so that it's directly above the subregion of this region Ri. Okay, so we've kind of, if we restrict the dimensions of the tangent plane so that it lies directly above this subregion Ri, but is still tangent to the surface at the point xi, yi. Okay, so if you do this, if you construct this tangent plane in this way, then the area of the tangent plane, I'll recall and keep in mind, right, that this is directly above Ri. Okay, the area of the tangent plane that's directly above Ri is approximately equal to the area of the surface lying directly above Ri. Okay, so if I've got this tangent plane up here, then what that's going to tell me is that it's the area of this tangent plane is approximately equal to the area of the surface that falls directly above this subregion Ri. Okay, and so we'll call that part of the surface Si. Right, so just to keep these things straight, this is Ti. Ti is the tangent plane. Si is the surface subsection. Ri is the subsection of the domain. Okay, and so all we've said so far is that this is a tangent plane that's built on at this point on the surface, right? So it's going to have the same inclination as the surface at this point. And we're going to restrict the size of the plane so that it's just directly above the subregion Ri. And if we do that, then the area of this regular old flat plane will be approximately equal to the area of the subregion Si on the surface. Okay, so what we're saying here is that delta Si is approximately delta Ti. Okay. All right, so these two pieces are about the same. Okay, so let's just make that clear. So what are we doing here? Well, we've got our Ti, which is a regular plane, right? And it's tangent at this point xi, yi. Xi, yi, zi. Right, the surface is what we're referring to as Ti. Now, it's touching the surface, right? It's touching the surface. I drew it above it, but it's technically would be touching that surface at just the point xi, yi, zi. And then underneath it, of course, is some curved surface, right? Ti is a plane, but Si is, a curved surface that is part of the surface S, which is denoted by the function f. Okay, and all we're saying is that the size of Ti, the area of Ti, is approximately the area of Si. Okay, approximately. Okay, and so this kind of sets up the idea that, well, look, if the choice of xi, yi is totally arbitrary, so it turns out that, the sum from I equals 1 up to n, there's going to be n si's, should be approximately, I'll put approximate there, approximately the same as the sum from I equals 1 to n of delta Ti. Right, so all of the little tangent planes, the area of all the little tangent planes all over the surface that you would get by repeating this process for every rectangle in the region, each one of those is going to be approximately equal to the SI that corresponds to it, and so the sums would be approximate as well. Okay, so this is going to create our approximation, right? Because it's very easy to identify the area of a plane when it's a flat plane like Ti is, but it's not easy to identify the area of a curved surface Si. Okay, so how are we going to identify the area Ti? How to identify the area of Ti? Well, we're going to, first of all, take note of the fact that the sides of the, well, I'll take note of the fact that, okay, a couple things to notice here. So notice first that Ti is a parallelogram. It may be rectangular in some places, but depending on how the plane sits relative to the region below it, the angles will be potentially exaggerated, right? But it's always going to fit the definition of a parallelogram: opposite sides, opposite angles equal. Opposite sides equal, opposite angles equal. So it's a parallelogram. And the sides of this parallelogram can be identified. Right, the sides of the parallelogram can be identified. We'll call one of them U, and it's going to be equal to delta xi in the I direction plus f sub x xi yi delta xi in the in the k direction. Okay. And the other side, so this is maybe this is the long side of the parallelogram. The short side which maybe we'll call V. And again, this is long and short. It doesn't matter. Parallelograms will tend to have, opposite sides. So maybe we'll call this one U. This one will be V. V is equal to so it has a similar formulation. It'll be delta yi times I plus partial with respect to y delta yi times k. Okay, so these two here give you the sides of, and again, this is ti. Okay, and so if we think back to a earlier chapter when we were talking about the cross product, we should recall that we can use the cross product to calculate the area of a parallelogram if we know the adjacent sides. In particular, the norm of the cross product of two vectors will be equal to the area of a parallelogram having U and V as adjacent sides. Okay. All right, so this area here can be calculated by crossing U and V and taking the norm. Okay. And so that being the case, then we can come up with a general expression for the area of each of these TIs. Okay, so the area of delta TI is going to be equal to this. All right, so let's calculate this. We'll start by just doing U cross V. Okay, and so for that we're going to need I, J, K. All right, and so the I component is the delta X, delta Xi, and then you've got 0 for the J component, and then you've got the partial with respect to X for the K component. And so this would be your U, and then similarly for V, you're going to have a 0 here, but a delta Yi, and then an F sub Y, Xi, Yi, delta Yi here, right? So what we need to do is calculate this cross product. Okay. And so we remember how to calculate the cross product. We're going to need the I component, J component, K component, and it's done by kind of crossing, so cross multiply and subtract the two products. Right, so going through this, we would say the first one would be, what do we get here for the I piece? We would get negative F sub X, Xi, Yi, right? So we're crossing this out, and so that's 0, and then it's just minus that. And then delta Xi, delta Yi, and that's the I component. And then minus, and then we do the J component, we cross that out, and we would get minus F sub Y, Xi, Yi, delta Xi, delta Yi. That's the J component. And then the K component, we cross this out, and it's just the product of those two. So it'll be delta Xi, delta Yi, times K, the K vector. Okay, and so we can simplify this somewhat. So this whole thing can be simplified down to the following. Basically, we can factor a delta Xi, delta Yi out of each of the terms. And a simpler way to write this would be to write it like this: negative F sub X, Xi, Yi times the I vector minus F sub Y, Xi, Yi times the J vector, and then plus just K. Okay, and that's all going to be times delta xi, delta yi, which was what? Delta ai. Right, so these three, just to make sure people are following, these three have to be factored out. Okay, and so then you get this. So that's the cross product, but the area to get to the area, we really need to take the norm of the cross product. So we have to take the norm of this. So what does that look like? So the norm then of u cross v is just equal to the square root of the components of this thing squared. Okay, and so that's going to be f sub x, xi, yi, right? We're going to square that, plus f sub y, xi, yi. Now we're going to square that, plus 1. Okay, and then the delta ai is just a constant, so it kind of comes out, and the whole thing is a square root. Right, so this is technically like, looks like that, doesn't it? Okay, and so this gets us a nice expression for the area of each of the TIs. Okay, and so the surface area, we'll call it S, is approximately equal to the sum from I equals 1 to n of all of the little surface areas. Right, those little subsections, right? Remember we had our plane, our tangent plane, and then each of those corresponded to some actual section of the curve. So you had your TIs and your SIs, right? So we find an approximation for each of the SIs, add them all up, that's an approximation for the total surface area. Okay, and then we just said that delta SI can be approximated as the sum from I equals 1 up to n of this thing. Okay, and so let's rewrite that. I'm going to put the 1 up front. 1 plus f sub x, xi, yi squared plus f sub y, xi, yi squared. Okay, take the square root of that whole thing and then multiply it times each of the individual areas. Xi, yi, okay. Okay, and so this is obviously going to bring us to how we define this in terms of a double integral, because this looks an awful lot like a Riemann sum. Okay, so let's go ahead and define the area, the surface area, via double integral. Okay, so definition. If f and its partial derivatives are continuous, okay, on a closed region R, in the xy plane, okay, then the area of the surface S given by z equals f of x, y over R is given by, right, and so it's a simple thing here, the surface area equals the double integral over the region ds, right? So d would be this would be the surface area, okay, and then of course we can expand the ds here into the actual formula, and so here we'd have 1 plus f sub x xy squared plus f sub y xy squared. And you don't have much space. Can I get it in there? Yes, dA. Okay, perfect. Okay, and so that's the surface area in terms of the double integral. Now, you may be looking at this and there may be something kind of sparking in your memory from back in Calculus 2 days when we were talking about the length of a curve, okay, arc length, right, from Calculus 2. Okay, so you might be remembering that, and so it turns out that this idea here, this formulation for calculating the surface area, is pretty much perfectly analogous to the definition of arc length from Calc 2, right? So if you think about it like this, in Calc 2 we had the length on the x-axis, right? And we would have calculated it like this from a to b of dx, right? So simple thing. But then we had a length in the xy plane. Right? To calculate a length in the xy plane, we would have said ab times ds, which is the same thing as a to b, integral from a to b of 1 plus f prime of x. Remember, we squared the derivative, took the square root dx. Okay, and so this is what we did back in Calc 2. Now in Calc 3, we have the idea of a double integral, and so we can derive something really pretty analogous. So in Calc 3, we have the area in the xy plane, right? The double integral over a region in the xy plane. So that's a double integral, so dA. Okay, and that can be extended to the surface area in space, which is the double integral ds. Okay, so you take this, and then it has a similar formulation to what we see in this one. It's equal to the double integral over r of 1 plus f sub x xy squared plus f sub y xy squared, and then dA. Right, so you see how this guy here and this guy here are kind of similar, right? And they both sort of are, they take the simple idea and blow it up into the kind of the next higher domain, right? So here we take the simple length on the x-axis and we blow it up into a length of a curve in the xy plane. Here we take the area in the xy plane and we blow it up into the surface area of an arbitrarily curved space, a surface in space, right? And you can see both of them incorporate the derivative into the integrand. Okay. So that's the idea. So this is the big formula. The surface area is equal to the integral over the region. It's 1 plus the partial with respect to x. You have to square it, plus the partial with respect to y. You have to square that as well. Take the square root of that whole thing and differentiate. Integrate with respect to a. Okay, so this is the idea. Now it turns out, as you can imagine, just by looking at the structure of this integrand, it turns out that a lot of time, most of the time, the integrals for surface area are difficult to calculate. They can be very challenging to calculate, in fact, and it's just because you're taking a partial square. I mean, any function that has even moderately complex partial derivatives can be very challenging to calculate. And then in addition, you have a double integral where the inside integral is going to have a function as bounds, right? So that those two factors they kind of combine to make these sorts of integrals particularly challenging, right? But there are a handful of cases and types that are pretty easily evaluated, and let's do an example. We'll kind of begin with that as an example, right? So let's do let's do this example. We want to find the surface area. Find the surface area of the portion of the plane. And this is a particular plane. It's not one of the not one of the axial planes. It's z equals 2 minus x minus y. All right, so we want to find the surface area of the portion of the plane, z equals 2 minus x minus y, that lies above the circle x squared plus y squared less than or equal to 1 in the first quadrant. Okay, so what the heck does that look like? All right, let's try. Let's try to draw it here. So if I've got my z-axis, and I've got my y-axis, and I've got my x-axis. Okay, and and so you can see this, the region of interest is x squared plus y squared equals 1, right? That's the circle. And so I'm just gonna, and we're just interested in the first quadrant, right? So that's gonna look something like this. It's not a perfect picture, of course, but it looks something like that. And now this surface that we've drawn is gonna intersect the x, y, z axes at particular points, right? And so it's gonna kind of pop in here, and here maybe, and then over here somewhere. Right, we'll get to exactly what all these points are in a moment, but I'm just trying to sketch the picture. Right, and so this is technically going to be above, yeah. Maybe we'll draw this kind of more like this, actually. Forget that outer one. We'll say this is it. So this is x equals 1, this is y equals 1. Okay, and so somewhere on this surface, we're going to have a kind of a top to this thing. And that's the part that we're interested in. Okay, so we're interested in just this top. It's kind of like a triangle, but it's got a curved outer edge. Okay, it looks a bit like this. It's kind of like a pizza slice, kind of, but it's yeah, kind of like a pizza slice, maybe. Okay, so that's the piece we're interested in. Terrible drawing. Apologies, terrible drawing. But this is the part that we want to know the surface area of. Right? Now, what makes this kind of easier than a typical kind of problem is that the partial derivatives are constants. Right? So f sub x, xy is just -1. F sub y, partial with respect to y, is just -1 as well. Right? Just pull those right off of there. And so the fact that you've got constant partial derivatives makes the function relatively easy to deal with. Okay, and so the surface area here, we can go ahead and calculate, or I can set up the integral, right? So we know it's going to have this formula. And I kind of abbreviate this now, otherwise it gets kind of redundant writing that whole formula out, but I do want to write it out so people know where things are coming from. But I can leave the xy's out, right? Okay, and so this is just going to be, in this case, equal to 1 plus -1 squared plus -1 squared, square root of that. And so this is a straightforward, it's just a constant. Okay, and so in this case, what are we looking at? Well, this is basically just the square root of 3 times this double integral dA. Right, so pretty much it's just square root of 3 times whatever the area of the region R is. Right, and so the region R, remember, is just a quarter circle of radius 1. Right, so the region, so we've got square root of 3, and then this piece here is just, again, the area of the region. and it's 1/4 of a circle of radius 1, so it has area 1/4. Right? And so the area of the guy on top is the square root of 3 over 4. Okay. Oh, I'm sorry. This should be pi over 4. What was I writing that for? So, okay, just to be clear, this where did this come from? So this is just, remember, this is going to be the area of the region, right? The area of the region is 1/4 of the area of the circle, and in this case, the area of the circle would be pi times the radius, which is 1. So it's pi over 4. Right, so this should be square root of 3 pi over 4 is what I meant to write there. Okay, so that's the area of the region down here. And what we've found is that because this has constant partials, this basically just becomes a constant times the area of the region, right? And so that's why this one is relatively easy to sort out. Okay, but that won't always be the case. In fact, if the surface isn't if the surface of interest isn't a plane, then you won't have constant partials, right? So let's do an example where we kind of ratchet up the difficulty a little bit. Okay, so let me get a new page here. Let's get a new page here. So let's say we want to find the area of the portion of the surface the portion of the surface, and the surface is f of xy equals 1 minus x squared plus y. We want to find the area, the portion of this surface that lies above the triangular region with vertices. Okay, so we'll have 1, 0, 0, and 0, negative 1, 0, and 0, 1, 0. Okay, so that's the problem, right? So we've got some surface. This is not a plane. You can see that. It's going to lie above some region that has these as its vertices, and we want to know the area, the surface area of this surface here above that region. So first of all, let's find the partials. All right, so the partial with respect to x is negative 2x, and the partial with respect to y is 1. Okay, so these are not too difficult of partials to deal with, obviously. Okay, now let's try to draw a picture of, well, let's just plug this into the general, let's plug these partials into the general formula for the surface area. Right, so that's a double integral over the region, and obviously we'll have to come back, draw a picture to figure out what the region looks like, but we know that that's the formula that we're interested in here is 1 plus f sub x squared plus f sub y squared dA, dA. And that's going to be, in this case, partial over r, or sorry, the double integral over r, and it's going to be 1 plus, we square that, we get 4x squared, and we square that, we get 1. And then finally we can simplify this down, and this is just going to be partial over r, sorry, the double integral over r, and it's going to be 2 plus 4x squared. And we'll leave it as dA for now. Okay, dy dx, how we're going to go about this, it's not clear yet, but let's leave it like this for now. So let's draw a picture and make sure we can understand this region, because you sort of have to have a picture or some sense for what the region looks like before you can identify the bounds, like before you can sort out what the bounds need to be. Okay, and so for this one, I'm going to draw it kind of like this, And I hope this is interpretable. No, this will be fine. There's your y's, there's your x's, and then z comes out the top. We'll get to that in a second. And so we're going to have some triangular region, right, in the xy plane that is going to look a bit like this. Okay, so you've got basically this triangular region. It's the positive x-axis, and that's the positive y-axis. And so you got this triangle here. Okay, now this one actually goes through -1 on the y-axis, and this is the other vertex is at 1 on the x-axis, and then this vertex up here is 1 on the y-axis. And so remember, this information was given here, right? So you got 1 on the x-axis, -1 on the y-axis, and +1 on the y-axis. Okay. And so this obviously lies in the xy plane, right? Kind of goes without saying to some extent. And then above this, there's going to be some surface. Okay, and so I'll try to draw that. So it's going to look kind of like this. All right, so we've got the z-axis here. Okay. Right, so you can see this, and it's not drawn great, but this is supposed to be kind of under here, right? And so this is the surface that lies directly above this triangular region in the plane. Okay, so you can imagine it kind of coming off the page here. Okay, and so when we look at the region, we have to think about bounds, like how can we what do the bounds look like for a region like this? Well, we've got a couple lines here that are easy enough to identify. This line here, this is going to be y equals 1 minus x, right? And you have to kind of do a little mental gymnastics, but you notice this is the positive x-axis, and so the y-intercept here is at 1, and it's got a slope of -1, right? It comes down, and the rise over run is -1 over 1, right? So the slope is -1. So this line here is y equals 1 minus x. Now what about this line over here? Well, this line is y equals x minus 1, right? And similarly, you have to kind of take the thing and rotate it in your brain, but this is the y-intercept at -1, and you can clearly see that the slope is positive in this direction. It goes up 1 over 1, right, in order to go from here to here. And so it has a slope of +1. Okay, and so what we can do is we can see that the bounds for this, we can see what the bounds are for R, and in particular you can let you can let x range from 0 up to 1, right, from here to here. And then the y bounds are going to go from this line up to this line. Right, and so that means x minus 1 is less than or equal to y, which is less than or equal to 1 minus x. Okay, so hopefully that's clear. So you've got x is going from the origin over to 1, and y is going from this line up to this line, right? So it's going to go like that, and then the x's go like this. Okay. And so this kind of a setup, just given that the constant bounds are on the x, means we're going to be doing a dy dx integral. Okay, and so we can take this guy up here and we can rewrite it with the bounds. Okay, and so that means we've got the integral, the double integral from 0 up to 1, and then from x minus 1 up to 1 minus x of 2 plus 4x squared dy dx. And so that's our double integral. Okay, and so integrating with respect to y first is very simple, right? This is just a constant, so you're going to have 2 plus 4x squared. And then you're just going to toss a y in there, and that'll go from x minus 1 up to 1 minus x dx. And so evaluating that inside piece, you'll have 0, 1, and then again just leaving the 2 plus 4x squared square root alone. And here we'll go 1 minus x minus 1. That's dx. All right. And so here we have 1 plus 1 and negative x minus x. So this becomes basically 2 minus 2x. So 0 to 1. And then you have 2 plus 4x squared. And then 2 minus 2x dx. Okay. Now this integral here is not, so a couple of things you can do with this. You can kind of break this piece apart, like some sort of distribute this constant, well, it's not a constant anymore, but distribute this radical through this expression. And you get 0 to 1 of 2 times the square root of 2 plus 4x squared minus 2x times the square root of 2 plus 4x squared. Right, and so you may look at this and you might think this is an easy, well, I don't know if you think that, but you could try some things with this integral, and you may think, oh, maybe I can do a u substitution with u equal 2 plus 4x squared, and that gets you this piece of it. This other piece is problematic, though. Right? It's hard, it's difficult to integrate this other side. And so what you can do, and this isn't something that we've probably had a lot of experience with, but it is something we talked about in Calc 2. You can use a table of integrals to find this form. So using a table of integrals, you can identify the following form. This integral would be equal to x times the square root of 2 plus 4x squared, okay, plus the natural log of 2x plus square root of 2 plus 4x squared, minus, and then it's 2 plus 4x squared to the 3/2 power over 6. And this needs to be evaluated from 0 up to 1. Right, so some of this you could get easily, again, about half of the integral can be identified quickly with using a u substitution. The other half is the tricky part. But there is a nice table form that this fits. Okay, and so what do we get when we evaluate this? At this point, we're kind of through the surface area piece of the problem, but let's go ahead and run this to its conclusion. What do we get here? We get, well, evaluating the upper limit first, we get 1 times the square root of 2 plus 4 times 1 plus the natural log of 2 times 1 plus 2 plus 4 times 1, okay, minus 2 plus 4 times 1, 3/2 power over 6, right? That's the top. And then at the bottom, a lot of these things are going to zero out. So the first term is going to be 0, right? This is 0 times this whole thing. The second term, you do get the natural log of the square root of 2, right? Because this becomes 0 and this becomes 0, and you're left with the square root of 2 in the middle. Okay, and then in the last section here, you get minus 2 plus 0, so this would be 2/6. Okay. Sorry, minus. Like so. Right, and then so the whole thing cleans up nicely, and you get the square root of 6 plus the natural log of 2 plus the square root of 6 minus the square root of 6 minus the natural log of, and this should be, 3/2 power here. So minus the natural log of the square root of 2 plus the square root of 2 over 3. Right, so that's what you get down here. And so that is approximately 1.618 when you plug it in. Okay, so again, this one wasn't too difficult. The region was relatively easy to work with. It was a simple kind of triangle. Some pretty easy region. Let's take a look at another example. And this is an example where we'll pull in polar coordinates. Okay, so find the surface area of the paraboloid. And the paraboloid is z equals 1 plus x squared plus y squared that lies above the unit circle. Okay, and so the fact that we're dealing with a unit circle as the region, it makes polar coordinates an obvious choice here, so we're going to use polar coordinates. Let's start by drawing a picture of this thing. Okay, and so it's a paraboloid. It kind of looks like this. Okay, you got the z-axis right through the center of the top of the thing, and then it kind of comes down. It looks a bit like this. Maybe not exactly. Okay, and then somewhere below here, you have the XYZ origin, and you've got your x-axis, y-axis, and then you've got a unit circle down here that extends, we'll say like over to here, in the XY plane. Okay, so this is the unit circle. Right, so that obviously means this is 1, and this is -1 on the y-axis. This over here would be 1 on the x-axis, and then over here you would have -1. Okay, and so what we're interested in is, so this would extend indefinitely, but what we're interested in is just this part because it's the part that's above the unit circle. Okay, so we want to know the surface area here. Okay, so this problem benefits very greatly from polar coordinates. Okay, and so the region of interest is, the unit circle. So 0 less than or equal to r less than or equal to 1, and 0 less than or equal to theta less than or equal to 2 pi. Okay, what are the partials of f? F sub x is equal to 2x. F sub y is equal to 2y. Right? Again, just differentiating the function with respect to x and then with respect to y. Okay, so we've got a relatively good setup here, seemingly. So let's plug all of this into the integral, into the formula for the surface area, and see what happens. So the surface area is going to be equal to this double integral over r. And then again, just to drive this home, it's partial with respect to x squared plus partial with respect to y squared plus 1 dA. And so we can just plug everything in here, right? This would be, in this case, we'll go with just plugging in the function first. So this is 1 plus 4x squared plus 4y squared dA. Okay, and then we can convert this to polar form, right? So wherever you see x here, that's going to be r cos theta. And wherever you see y, that's r sine theta. Okay, and so we can set this up. The integral will go from 0 to 2 pi, and then from 0 to 1. Right? So the radius is the inner integral, the theta is the outer integral. And then the function will be changed into, remember we have to toss in an r factor, so just do that up front. So it's going to be 1 plus 4 times r squared cos theta plus 4 times r squared sine theta. And then it's dr d theta. Okay. And we can simplify this before we start trying to integrate it, just leaving the r up front here for now. if you factor a 4r squared out of these two, you get, oh, these should be squared as well, cos squared theta, sine squared theta, sorry about that. This would be cosine squared theta plus sine squared theta, and so those two together are 1. So if you factor this and this out, you get basically 4r squared times 1. And so the inside can be really greatly simplified down to 1 plus 4r squared. Right, that's just the Pythagorean identity there. Okay, and can we integrate this? Yeah, we can use like a u substitution on this. You could use u equals 1 plus 4r squared, right? And so just to kind of look back at that for a second, u equals 1 plus 4r squared, then du is equal to 8r dr, and du over 8 equals r dr. So you have the r dr here, and then this is just square root of u, right? And so what you have here is the integral from 0 to 2 pi times the integral of the integral of 0 to 1 of the square root of u times 1/8 du d theta. Okay, and so it would be probably the best idea here to maybe rewrite this one more time. 0 to 2 pi, and then it's 1/8 square root of u du d theta, like so. And then we just have to integrate with respect to u. Oh, I lost one there. It should be 0 to 1 as well. And so this, when we integrate with respect to u, this becomes 1/8 times 2/3 u to the 3/2 power, and that needs to go from 0 up to 1 d theta. Now it's important to notice here you don't want to just plug 1 into u. You have to convert u back into r first. And so this is 0 to 2 pi times, and this will be what, 1, so that'll be 2 over 24, so 1/12, the square root of 1 plus 4r squared. Okay, so 1 plus 4r squared, and then that goes from 0 up to 1 d theta. And so a lot going on with this one. So this is just going to be basically when I plug in 1 and 0 into this. So first I plug in 1, it'll be 1 plus 4, so that's just like the square root of 5, right? So you're going to have, oh, sorry, it's to the 3/2 power. So, oh, shoot, I'm so sorry. I made a mistake there. Let's back up a second. I miswrote that, so it should be 1/8 times 1 plus 4r squared to the 3/2 power from 0 to 1. Okay, d theta. Yeah, I wrote this as the square root. This is the 3/2 power, so that makes a big difference. Okay, so 0 up to 2 pi, and then 1/8, and then let's do the subtraction. So this will be 1 plus 4, so basically 5 to the 3/2 power, right? And then minus 1 plus 0, and then so it's minus 1 to the 3/2 power d theta. Okay, so whatever, it's all a big constant here. So this would be 5 to the 3/2 power is basically 5 times the square root of 5. Let's rewrite it one more time just to make it a little simpler before we finish it. So it'll be, and this should be 1/12. Sorry, geez, making a lot of typos here. 1/12. So that'll be 1/12 times 5 square root of 5 minus 1. Okay, so you've got this constant here, d theta. Okay, final step is to integrate that. It's all a constant, so you just add the theta in. So you've got 5 square root of 5 minus 1 over 12 times theta, and theta has to be evaluated from 0 up to 2 pi. And so what you get is 5 square root of 5 minus 1 over 12 times 2 pi minus 0. Okay, so it looks like this. Okay, and we could simplify this, of course. Probably minimally you could say this is 5 square root of 5 minus 1 times pi over 6, like so. Okay. So I think that should do it. There are, you know, so we did kind of a cross section of problems. Some of the problems are easy, some of the problems are harder. In general, surface area problems tend to be more challenging. Polar coordinates are a big help in basically, allowing the inner bounds to be more straightforward when the region is complex, or when the region is circular, but those tend to be like more complex regions. So polar coordinates can help make these easier, but in general, like the idea here is to just expand that double integral to the surface area, similar to the way we expanded integration generally to calculate arc length in calculus 2. And so very analogous kind of result here. Okay, so I think that'll do it for this section, and then next time we will begin. I think there's only going to be 2 lectures remaining of the course, and they're both going to be over triple integrals. And so we'll take the idea of the double integral and expand it one more time and come up with what's called the triple integral. And triple integrals they sound very, very scary. I know when I was an undergraduate, the kids who had already taken Calc 3 were all like, wait till you see a triple integral. They're not that bad. I don't think they're, you'll see. They're nothing to be feared. They certainly sound scary, but I don't think they're any worse than double integrals in the main. So, all right, we will see you all next time. Take care.